Okay. So welcome back to corrosion. Let's pick up where we left off last time. And that is discussing the non-perfect nature of metal surfaces that allow for anodic and cathodic reactions to occur on the same surface. So we talked about how grain boundaries can actually be the site of corrosion as well. We talked about the result of the corrosion in which we can see pitting, as you can see here. So yeah, so we can, so we talked about pitting and how some of the cracks that form, they'll crack right through the grains along some crystallographic direction. So that's granular corrosion. There can also be some de-alloying here. Or sorry, they can be in between, in between the grains. And so what that means is the electrolyte can come in and seep through all the, seep along the grain boundaries where the imperfections are. Right, and we talked about how when you have de-alloying, it results in all these, these non-uniform pits. And while most of the time that it's pretty bad, right? You lose material, there's pitting, that's not desirable. But if you can design the process in a way where you have two dissimilar metals and you can de-alloy one of the materials to get some sort of design geometry, some engineered geometry where you want these crevices to happen. And one of the examples that I gave was the example of battery electrodes, where you can have two metals, and then you can de-alloy one of them, and what's left behind are these pits. And what you can do is then put in your active material in the pits, and the liquid electrolyte in the battery can actually penetrate those surfaces better and actually deliver the electrolyte that's needed to make a battery work better. So there are some advantages if you can design your corrosion well to make whatever part you're trying to engineer. But obviously we are talking about corrosion as it affects a material where perhaps you didn't design your material to corrode in that way. And so what we want to know is, how do we control, or how can we also predict rates of corrosion so that we can check on materials and obviously replace materials before fatigue and failure of a part. Okay. So what does localized corrosion look like? Right, so this local attack, if you have a certain area where corrosion is concentrated, the local attack can happen at a rapid rate, and it can be really difficult to detect. And one of the questions that came up, I think, during the lecture and towards the end of the lecture as well last time, is that how do we detect corrosion? How do we attack crack formation? There are a number of ways. You can do visual inspections while the material is in service or the part's in service. You can also take a part that you want to reuse again and do X-ray diffraction, X-ray microscopy. You can also do magnetic imaging, ultrasound, because if you design a material to a certain thickness, and it will behave and respond differently to an ultrasound if it's a thinner piece of material over time. So there are a number of ways in which you can take apart a device and look at it and look for corrosion, and there are non-destructive ways as well, like X-ray microscopy. You can just take it apart off of the component, off of the ship, part off of the aircraft or something, and do X-ray analysis on it. Yeah. But and you can try to detect this localized corrosion so that we can avoid things like unexpected and catastrophic failure. Okay. So what makes something a localized corrosion? Well, it's localized if the dissolution of small local areas on the metal surface. So we talked about how aluminum become aluminum ions. So that area where the aluminum becomes dissolves and becomes aluminum 3 plus, that's one example. So while the other areas remain unattacked. Okay, so what can actually happen? Well, on a surface, you can have pitting, which is what we talked about. So local dissolution will leave behind shallow or deep undercut pits, dimples, craters, you know, these different geometries on the metal surface. It can also be intergranular. So that's what I was talking about before, where the electrolyte, you know, could be salt water, could be some acid. It could penetrate, you know, along these grain boundaries and basically start to break apart the material along the grain boundaries. And then what happens next is exfoliation. So once you break apart your material, these flakes of your metal starts coming apart and the material exfoliates. And so you could see that here, you know, these flakes are coming off. And typically that's not a good thing because you're losing material. The structural integrity of the material is being lost. It could also happen in a shielded or occluded area. So what that means is, let's say you have a bolt, you know, if you can actually create a crevice and cause crevice corrosion where there's local dissolution in an area that's shielded away from a bolt surface, and it can contain, you know, smaller volumes where you can concentrate that electrolyte. So you see this, you know, where you have rivets or bolts where on, let's say, ships, airplanes, where there are lots of these parts, you could really concentrate that environmental corrosion and basically expedite the rate of corrosion. And typically that is quite catastrophic. So let's talk about how we quantify, you know, the amount of applied current and the flux of a material. So here, if you remember, flux and flux of atoms within with the units of moles per centimeter squared here, what you'll notice is that now we'll talk about current density. So basically, this is Faraday's law that relates, you know, the current density that's applied over that area with units of amps per centimeter squared. And we're going to talk about the number of electrons that you've moved, right? Because before we were talking about, once again, the example of aluminum to aluminum 3 plus, we moved 3 electrons. So we want to be able to quantify that in an entire system. And so we can relate that, that flux to the current density and the number of electrons by converting the units, and that unit conversion is using Faraday's constant. And so Faraday's constant is just 96,485 coulombs per mole, or per some equivalent, right, so per electron. And so so that allows us to quantify the flux of the material that's moving, and also the number of electrons that are being passed. And so here's the example of aluminum going to aluminum 3 plus moving of 3 electrons. So here N would be 3. In the example of iron 2 plus, N would be 2, right? So we would see the flux be dependent on the current density and also the number of electrons. And so as you go on and learn more about, you know, corrosion in an intro to corrosion class, advanced corrosion class, you'll then derive other parts of Faraday's law to then manipulate it and then convert it into other equations where you can calculate how much material do I lose over time, or how many electrons am I moving over time. And so here are some of the other forms of Faraday's law that we won't derive, but I just want to show you to demonstrate what you can get out of manipulating this equation, right? So if you want to know, okay, how much mass per area, you know, is being dissolved, what's the corrosion rate for that, we can then manipulate that. And so you could see here the mass per area, M over A. You can see that by taking the original Faraday's equation as a function of time, and also molecular weight or the weight of the material. And then here we can also see thickness as a function of time. And so the thickness that's changing over time, we can once again manipulate Faraday's equation multiplied by the weight divided by the atomic weight divided by the density, or we can calculate the mass over time. And so you could see here that these equations are just related to each other by just moving around the variables. And then something that's described in your book is this corrosion rate. And it depends on which units you want to use. So here it's mils per year, right? And a mil is 0.001 inch. And so if you want to talk about corrosion rate in mils per year, then you use 534 times the weight loss in milligrams divided by the density times the area times T in hours. Okay. There's also in your book, you'll see if you want to discuss the corrosion rate as a function of millimeters per year, so mm per year, then this prefactor is no longer 534, it's 87.6, and you change your units of area from inch squared to centimeter squared, right? So depending on which units you prefer to use, the equation changes a little bit, and it's just derived. So these numbers are worked out and the units are converted so that you can just plug it in, plug in the weight loss in milligrams, how long it takes you, the area of the material that you're looking at, the density of that material, and then whether or not you want mils per year or millimeters per year to come out of it, right? And so that's just all industry-based type conventional units. Okay, so now we're going to talk about, which material is more likely to corrode. And typically people talk about, is a material more noble or is it more active? And so we can refer, and if we just think about thermodynamics, we haven't talked about galvanic series, which we will, where we take into consideration the kinetics of the reaction, of the electrochemical reaction. But here, let's first assume we're just looking at the thermodynamics, and we look at what we typically refer to as the standard electrode potential table here, where we can look at different types of materials, how many electrons are being moved, and then what is the EMF, right? What's the potential that's needed versus a standard hydrogen potential. And so the definition of just a standard hydrogen potential, or SHE, is that it's hydrogen plus 2 electrons going to make H2, or sorry, proton, H plus plus H plus plus E minus going to 0 valent hydrogen. Okay, so that's just the standard. That's what zero, here we go. That's what 0 is by definition, convention. Okay, so reactions that are closer to this N are more active, so they're more likely to corrode. You see elements up here, they're more noble, they're less likely to corrode. So you see the elements that you have some intuition for in terms of reactivity, right? So gold, platinum, silver. So these elements tend to be less corrosive, or they're less likely to corrode relative to the other elements on this reaction, right? And so what are the conditions in which we're doing all these tests by? So here you have, let's say, an example of iron going to iron 2 plus and 2 electrons. Okay, so let's look at that. When we talk and measure these potentials, what we're really saying is this metal, I have pure metal, I don't have any impurities, right? Which we of course know that's not realistic. All materials have some sort of impurity, some level of vacancy concentration, maybe some impurity level. I mean, we have processing techniques where we can get very close to high purity, like 99.99999. I mean, you can buy materials out to that level of precision. and that level of ultra high purity. But in reality, there's always some, percentage that is some very low impurity concentration. But theoretically, when we deal with these equations, we're concerned that we assume that the metal electrode is a pure metal, okay? And then what about the electrolyte? Well, the electrolyte, we assume that then the metal ions in the concentration, in the solution has a concentration of 1 molar. And 1 molar is 1 mole of that Fe2 plus in 1 liter of solution, right? So that's by definition 1 molar. That's what we assume. And then any gas evolution. So when we talked about, let's say iron in HCl, a hydrogen that's evolving, that is, or aluminum in water, evolving hydrogen and producing aluminum oxide, right? We assume that the amount of gas that's producing is at ambient pressure. So that's 1 atmosphere. And so we compare everything to standard hydrogen electrode. So all of this can just be shifted. So you can see here lithium plus 1 electron, lithium ion Li plus 1 electron going to lithium metal. You could see here that's negative 3.04 volts. So you could see then if I were to like arbitrarily not express this in standard hydrogen electrode, I would just shift everything by 3 volts, 3.04 volts up, right? And so it's all relative. So what you see in the literature is, of course, people have to write, this is, the potential versus the standard hydrogen electrode. Or typically in battery, like lithium ion batteries, people will shift the voltages by 3.04. And so what you really see on the y-axis is volts versus lithium / lithium plus versus this potential right here, right? So all it takes is just reading the y-axis and knowing the relative potential references, right? And so of course you would vary, if you're not doing your reactions and your experiments at these under these standard conditions, that's perfectly fine. And we can look at how to manipulate that so that we can adjust for differences in concentration and differences. If you're not comparing to standard hydrogen potential, you just shift all your potentials, okay? But this is at a bare minimum what it means to be standard. Okay, so then let's look at also what happens when 2 different materials are in electrical contact. So before we said these 2 dissimilar metals need to have an electronic pathway so that these electrons can be moved, right? And so in this situation, you can have galvanic corrosion because both of them share, they both sit in the same electrolyte here, and there's an electrical pathway that you see here. Now, if they were isolated like this, there wouldn't be any galvanic corrosion. If they were in separate containers, not in the same electrolyte, also would have galvanic corrosion. Right? So the 3 requirements for galvanic corrosion to occur is that electrical contact in the presence of a common sufficiently corrosive electrolyte, okay? And that's also listed here. So once you have this setup, then you're going to have galvanic corrosion, which if you have 2 dissimilar metals here, let's say you have aluminum, let's say you have some sort of iron here and they're touching, you could see that at the anodic site, you see quite a bit of pitting here that's happening. You can also see it in this micrograph of the pitting occurring at another site here where it's in contact with the iron. So you could see quite a bit of aluminum pitting in this alloy that's riveted to 980 steel sheet. So that's iron with some chromium, some molybdenum, okay? All right. So let's say they're not coupled. You can see here they're intermittently touching here, but let's say there isn't, if they're uncoupled in some way. Well, you can still have some gas evolution or oxygen reduction. So this is hydrogen evolution because H2 is in gaseous form, right? Here you can also have oxygen reduction to these hydroxides. So this is oxygen, so this is 0 valent, and this is 2 minus. So you can have oxygen reduction there. And so, but then if the metals are coupled, as I mentioned, right, then you can have the galvanic reaction where you can have metal dissolution at the anode. So then aluminum 3+ ions are being dissolved and going into the electrolyte. And what remains is, well, of course, aluminum, but it's now missing some mass, and that's at the pits. So before I talked about just looking at the thermodynamics and not looking at all at the kinetics. Well, the galvanic series takes a look at the kinetics of a system, and you may actually see a reversal in which materials are going to be more active or less active in this series. Okay. And so what you typically see for galvanic series data table looks like this, where now if you look at the potential, they're listed this way. Okay, so what you want to see is you want to look at the potential, and materials that are closer to this end are more noble. Materials that are closer to this end are more active and will be corroded when put up against a dissimilar material that's more noble. Okay, and so what I want to draw your attention here is magnesium here is quite active, zinc is quite active, so I'm looking at these potentials right here, right? Relative to what? Relative to graphite, relative to platinum, relative to other aluminum alloys, okay? Relative to silver, right? So I'm comparing where they are. I'm comparing where they are on this voltage list. Okay, and so we need to be careful because this list is a list of corrosion potentials in a given environment, right? So let's say if it's seawater, this is a list for seawater. So if you have different concentrations, if maybe it's not seawater, maybe it's water from a local river or what have you, you know, and you want to look at if you use this source and you have all these, you know, the concentration of different salts in this water, and you have some piping, you know, and you want to know, is this going to corrode my piping and cause not only pollution, but, you know, ions that I wouldn't want to be consuming that are neurological toxins. Then you have to do an entire standard series or look up data tables that someone else has already done, because you want to be careful that different elements will behave differently under different conditions. Okay, and so for the scope of this class, we're going to talk about materials in seawater and you know, environmental assisted corrosion. We also want to be looking at other controlling factors, not only, you know, what kind of environment it's in, like seawater, but we also want to look at the kinetics and also the cathode anode area ratios. Okay, so what do I mean by that? I mean, if you have a material, let's say, you know, aluminum versus, you know, some sort of titanium here, not only do you have to consider where they are, the potential, you know, is one active and one more noble. One would say, obviously, aluminum is more active and more likely to corrode. You know, the aluminum will dissolve, aluminum 3+, than, let's say, titanium. But what if you have a small area of titanium material and then versus aluminum? Or if you have a lot of titanium and you only have a little bit of aluminum, right? Relatively, even though aluminum is more corrosive, you know, it is more active in this galvanic series, you have to think about, okay, well, if let's say the aluminum does corrode, well, what's the limiting factor? When will the electrochemical reaction stop? Well, when you have no more aluminum, right? So if you have a little bit of aluminum relative to titanium, maybe you don't have to be as concerned, because once the corrosion reaction stops because you run out of aluminum, then there's no electrochemical couple, right? Then you just have titanium. So these are some of the more complex geometries and considerations and controlling factors that one takes thinks about, and not just, you know, is it easier, quote unquote, or more difficult for me to take away this electron, so it's more active or more noble. Okay. But of course, these additional factors you would learn about, let's say, in an intro to corrosion course taught by Professor Frankel or Professor Locke or Professor Schindelholtz in the materials department. Okay. So let's look at how these two data tables can be quite different, right? So here we, once again, you've seen this before, the standard, the EMF or the voltages for these different reduction reactions here, right? Where you have, let's say, so here you can see copper and let's say nickel here. You can see that sometimes in different environments like seawater, let's say here the galvanic series in seawater, you can see that sometimes materials can be flipped. Okay, so titanium here is more reactive, but here titanium is more noble relative to that of, let's say, nickel, whereas nickel here is more noble than titanium. Okay, so when you're doing corrosion rate studies in particularly seawater, you really have to consult these either these data tables or construct one for yourself in a standard way to really understand, you know, if a material is going to be more or less active. And just referring to this table is not always indicative, and sometimes it can actually flip your conclusion. So you know, would you be expected to know if nickel and titanium will always behave in this way? No, absolutely not, right? If you were asked about a galvanic series and comparing more active materials versus more noble materials, you would obviously be given a table like this with the exact environment that we're talking about, and say here seawater, because we're containing the scope of this course, but the scope of our discussion in this course. So you would obviously be given, you know, a table like this with the environment quite explicitly denoted. All right, so I talked a little bit about, you know, nickel and cadmium, say, and how you can couple the differences. So really what you want to look at, if you're just thinking about the thermodynamics, is you want to compare the potentials. And so since the potential of cadmium is less than that of nickel, you can see here that you can conclude that cadmium will corrode by just looking at the potential. So you can see here it's highly negative, and then it goes to highly positive. Okay. And I'll just talk briefly about solution concentrations. I know before we talked about, you know, 1 molar standard. So if you deviate away from these standard conditions, that's fine. You just have to take into account this perturbation term, where you take into account this natural log of the relative concentration of in the solution. So not a big deal. Basically, you take the difference and then you tack on this term to take into account temperature and also concentration differences. We won't go into that too much because obviously already there's a lot to deal with when we're just at standard conditions, but in case you might want to know for future reference, there is a way that we can manipulate Nernst's equation to deal with concentration and temperatures not at standard conditions. So if something's not at 25 degrees C or not 1 molar concentration of either of the two metals. Okay, let's get to environmental assisted cracking, because this is quite important in some of the examples that you see. So here, we've talked about how we use, you know, aluminum, titanium, steel, now lightweighting of material, so using magnesium. The issue, of course, is corrosion. How do these structural materials behave and survive in, you know, like what we talked about last time, like salt water or, you know, wintry conditions where you have salted the road, right? So we talked about pitting, intergranular growth, and then exfoliation of the material once the electrolyte seeps through along the grain boundaries and break apart the material, and you have these exfoliated sheets. Okay. So when you have stress and corrosion, one moment, oh, here we go. So when you have stress and corrosion, your time to initiate a crack will decrease. And what else can corrosion do? Well, it can increase the crack propagation rate, right? So your dA over dt, A being the crack length, right? So it can basically expedite time to failure quite rapidly. Okay, so here's some micrographs that you see where you could see here intergranular growth, and that's in real environment. And here you see the pristine material without any cracks, no embrittlement whatsoever, right? So what will happen? Well, when we talked about crack propagation, we talked about, okay, it can happen in a number, in 3 stages, right? Where you have initial, and then you have a steady state, and then you have where the crack grows exponentially here, and it grows really fast to K1C. And once it reaches your fracture toughness level, then it, will, your material will fail. Environmental assisted cracking, you could see here that number is much lower. So it reduces your fracture toughness to something that's substantially lower. So what you had, all those calculations you did before when you just made your material and it's going to go into some component, in some system, before we said, okay, well, we can sort of predict and we can look at, stress concentration and compare it to fracture toughness, and then we can predict if the material is going to fail or not. Now, if there's added issues like environmental assisted cracking, then that whatever calculations you did, well, that that failure can happen way more rapidly and sooner than you would anticipate. Okay. If you just looked at the pristine fracture toughness. So here's some example where you could see crack growth rate versus stress intensity factor, similar to the plot that you, the hypothetical plot that you just saw. And you could see here the material that's been collected in the Fontana Corrosion Center. You could see here the crack growth is increasing, and the material is failing well before what you expect. And here it's some particular electrolyte, 0.6 molar sodium chloride, so it's not 1 molar, but so there's some deviation from standard there. So, but the takeaway point is that this material is failing well before you thought it was going to fail, because of environmental assisted corrosion. All right, let me check on time to make sure that we can get to some of the example problems so that we leave time for that. But so I will see how far I can get with some of these examples, and then we'll dive straight into the examples. Okay, so the next set of slides are dealing with real-world failures, and our discussion of this is not obviously to highlight the failures, as in look at all these what had gone wrong, but more learn from what had gone wrong, and perhaps be better scientists and engineers and design better infrastructure and better components so that we can avoid this in the future. Okay, so it's not really to highlight any one particular catastrophic failure. It's just these are the lessons that we need to learn so that we don't repeat history. Right, so here's an example of the San Francisco Pier, the bridge right at Pier R2. So what had happened here is you can see here this, the failure, and the reason due to this, of course, they're all related to environmental assisted cracking, where stress has intensified due to the fact that all these posts that are in, there was like 4896 of them, in one of these cones. And what had happened, of course, is that they were in salt water, and there was hydrogen embrittlement, and that actually sped up the failure that since they were exposed to salt water and also rainwater. And so, you know, when we design a component, of course, we can do testing and modeling in the lab and calculate, you know, all the stress concentration and such. But what we really need to do is real life testing, accelerated testing, where we put these materials and these components into conditions that we think they're going to be exposed to, the environmental conditions, and accelerate that to see what's going to happen in X years, and of course check in on them to do all this testing. Okay. So we've learned quite a bit that from environmental, from, you know, to 2003, that we need to check in on materials and components that are in salt water and in rainwater, more so because, of course, their time to failure can be expedited. Here's a more local example. Similarly, you can see corrosion pitting that occurs, and so the failure of this bridge was also due to environmental assisted cracking from the from corrosion pitting that nucleated the cracks. Internal parts. So here's an example of pre-catastrophic pipeline failure in New Mexico, where this pipe was thinned and there was internal corrosion that wasn't detected. And of course, when the pipe ruptured, you know, the gas line was exposed and caused a pretty massive failure and explosion, as you can see here. And so, you know, what we can learn from this, of course, is how do we mitigate internal corrosion in a number of piping systems that are used elsewhere. And you can see some of these examples here. You know, this obviously hasn't happened since this one instance, which is pretty unfortunate, because there's, well, one, you know, this catastrophic failure, but also, of course, you know, a life was lost. And so, you know, there's some pretty real consequences when we don't get our engineering right. And this fuselage, as you can see here, it's missing a part. And, you know, this happened mid-flight. And that was really due to, once again, crevice corrosion. And it was pitting that was caused by stress concentration, and that initiated fatigue and then eventually failure. Okay. Now, obviously, we've learned quite a bit from this instance. And so obviously design of fuselages have changed quite dramatically since then. A really unfortunate recent example is the Flint, Michigan example, where water, you know, when they switched water supplies, also the new water supply was more corrosive. There were some inhibitors in the Detroit water that was flowing through these pipes in Flint, Michigan. And when, you know, that was switched and the piping, the Detroit water had some corrosion inhibitors, and the Flint water had higher concentrations of chloride ions. And so, of course, that, you know, led to some corrosion of the piping, which of course release lead ions in the system. And, you know, lead is a building neurological toxin. So over time, the accumulation of these ions have some pretty disastrous health effects, right? So it's not such ancient history that we need to learn from to design and know about the environment better. Here's another example of a situation where thinning of a component also, you know, due to corrosion, led to failure. So this was a ride at the Ohio State Fair just a few years ago, and you could see here, you know, that this component had cracked, and it was learned that when you when they took it apart for analysis, what was understood to have happened is that the walls were thin and due to corrosion, and that of course couldn't support the load that was applied, that was obviously past inspection initially. That was not the case anymore. Of course, what I know is from the public releases, but you know, that's something we can learn from as well, is these corrosion and thinning of materials can have quite catastrophic results that are pretty close to home. Now, I said before, you know, if we understand corrosion, we can understand and predict failure to obviously prevent loss of life, but we can also improve life and how people live if we can design corrosion in a way that is beneficial, right? So the corrosion is obviously the science of these electrochemical processes, and if you can understand how they work, you can design parts like, you know, like this implant that can be bioabsorbable. And so, you know, if you design a material to dissolve over time, it can actually help heal better, right? Have your tissues can go around that piece a little bit better than, and be integrated better. So, you know, it's really about understanding corrosion, understanding component design. So, all right, let me make sure I have some time here. So let's do the first example. Okay, let's do the first example here, where you have a piece of corroded steel plate. It was found, let's say, in a submerged ocean vessel. So you can see it's been exposed to seawater quite a bit. It was estimated that the original area of the plate was 10 square inches. Okay, so now we know the units, and so we now have an idea of the conversion rate equation that we should use in terms of which prefactor we should use. And it was approximately 2.6 kilograms that had corroded. So that's the weight that's been lost during the submersion. Assuming corrosion penetration rate of 200 mils per year for this alloy in seawater, estimate the time of submersion in years. And here we're given the density of steel is 7.9 grams per cubic centimeter. So we know corrosion rate is the prefactor K times the weight that's lost divided by density times area times time in hours. So what we really want to solve for is T. All right, but it's given in hours, but we need to calculate it in years. So we'll need to convert afterwards. So when we rearrange the equation to solve for the amount of time of submersion, we get right. So that's the corrosion rate. And so then we know, because here it's inches and also mils per year, we know that K is 534. If we were given in millimeters per year, we would use the 87.6 number. So we have 534 times, before I mentioned that this needs to be in milligrams, so we need to convert the kilograms to milligrams. And then density is 7.9 grams per cubic centimeters. Area is 10 squared inches. And the corrosion penetration rate is 200 mils per year. And so you could see, okay, well, I have centimeters here and I have inches here. You know, and I have grams here, I have milligrams here. Do I need to, you know, do dimensional analysis and make sure that these units work out? The answer is no for this particular equation, because that's all subsumed in 534. Those units have already been worked out for you. So you can actually just directly put into this equation and solve for T in hours. That's the standard unit for T here. And so what we get out is 8.8 times 10 to the 4 hours, which if we convert to years, we get, 10 years, okay? Or, well, I'm just rounding up, but yeah, so that's what you would get. So let me pause here and see if there are questions. What was the other number for K? It's 87.6. If your units were centimeters squared, and if this were given in millimeters per year. Those are the coupling, okay? And of course, they're both here. The mass loss, both, if you use 87.6 or 534, it's still in milligrams, okay?
So why were you able to use the density in centimeters cubed, but the area is in inches squared?
So if you convert this, you would get some factor, right? I mean, 1 inch is 2.54 centimeters. You would cube that, all of that. Well, you wouldn't have to do all of that because that's already subsumed in 534. One of the reasons why you're given those two equations, for corrosion rate, 534 or 87.6, is because you're locked into these standard units. So if you use another, like if you use, I don't know, something else that's not the standard conventional way of doing these corrosion analysis, then you would have to redo this equation and figure out what K is yourself. Now that's not standard, as in that's not conventional, so most people don't, but you use 534 if these are your units for density, grams per cubic centimeters, area in inch squared, mass loss in milligrams, and corrosion rate as mils per year. And so this table, I don't remember exactly what which table it is, but it is given in chapter 16.
Oh yeah.
Mm-hmm. Yeah. Okay. Next, let's just do something qualitative, right? So here, if you have a electrode reaction, and you're asked, well, okay, which material is more active and which material is less active or more noble? We talked about briefly, it's really just qualitative. You just look, okay, this is more active and this is more noble, right? So if you had this couple, which material is going to react and corrode? Well, it's going to be your sodium, right? And so this is particularly useful if you have, when you're really in the field and designing, right? If you have something like steel versus zinc, you look up, you look up the Galvanic series, and so you would go back and look at your table to do your design. So here, what you'll see is, if your ship is, made of some, it's mostly steel parts, what people tend to do is they'll put a zinc on the hulls, the bottom of the ship, to basically act as because it's the more active material relative to steel, that's where your sacrificial anode is going to be. And so zinc is going to basically be corroded. And so what you'll see is, these ships with these bars on the sides of the hull. And so what happens there is every 2 to 3 years, they just replace those bars. They do, obviously corrosion analysis to see how much mass was lost, obviously how active it has been. If it's been doing its job, then that material would be corroding. And, you're sacrificing some zinc versus the corrosion of your ship, okay? So basically just look at and compare the voltages. So in this, in the example that I gave here is obviously just on thermodynamics. And so, but the methodology is the same. You look at the electrode potential, and the larger the number here, positive as well, then that's going to be more noble. And this is going to be more active. Okay. Oh, interesting. Oh, there was supposed to be another slide. I apologize for that, everybody, because I wanted to discuss, excuse me, ooh, that was very loud. Let's do another example, because I wanted to talk about that before we wrap up. And I just want to leave a few minutes as well to do so. Okay, so let's do another example. Pardon. Let's do, okay. Okay, let's do another example where we look at failure analysis and corrosion. So let's take the example of a naval ship, and let's say a naval ship component has a material, has a materials property K1C. This is the plane strain fracture toughness of 26 MPa brute meters, and it has K1 EAC. So this is environmental assisted corrosion, or sorry, cracking. And its fracture toughness is much less than that, okay, due to the environment. And let's say the internal crack length is 4 millimeters. And let's say the geometric factor is 1 for, simplicity. So we want to know, will fast fracture happen at a stress of 200 MPa in a protected environment and also in seawater? Okay, so this is the value, the fracture toughness for in seawater. So let's look at then, in a protected environment, we can calculate the stress concentration concentration factor as, geometric factor is 1, applied stress is, let's say, 200 MPa, and this is square root, since it's an internal crack, it's 4 times 10 to the minus 3 divided by 2 meters. Okay, so I converted millimeters to meters, and I get stress intensity factor is 15.85 MPa brute meters. And so clearly, if we look at it in the in a protected environment, that's well below that of K1C, right? So that's below 26 MPa brute meters. So fast fracture will not happen. But if we compare it, if it's in seawater, then fast fracture will happen because that is above 10 MPa brute meter. Okay, so it does make a difference when you're looking at a component under, just inert environment, maybe in the lab or something like that, where it's not as exposed, and then or in a controlled environment. And then also, if it's in service in seawater, then we have to take that into consideration, in which case, K. So no, fast fracture won't happen here. In inert environment. But here, it is greater than this K1 EAC, and thus fast fracture will happen in salt water. Okay, so 2 conditions that will change your answer. Okay. All right, with the time remaining, since this is my last lecture, I will be on the Zoom call for the class session on Wednesday, but Professor Glenn Dane will be giving the lecture on societal and environmental impact. So I will not be giving that lecture, but I'll be present the entire time. But since I won't be giving the lecture, I just want to say, thank you, everyone. And, it's been quite a privilege and a treat. So with that, good luck with the rest of the semester. All right, we can adjourn here, and I'll take a look at the questions that were posted since the last time I checked. So let's see. Okay, yeah, so the question, is it desirable to plate a metal that corrodes with an active element that will form an oxide layer like steel-plated zinc that you mentioned? Oh yeah, so yeah, that's just to take into account the galvanic series in comparison of, you know, if a material is more or less active. And correct, that does not have to do with the passivation layer per se. And I think what you're referring to is the native oxide passivating layer that typically forms, you know, on zinc oxide. So you'll always find maybe a few nanometers of zinc oxide on zinc if it's just left alone and you haven't reduced it. And then, yeah, same thing with aluminum. So let's see, what is happening on Friday? Yeah, no, well, there is no lecture per se, but similar to exam 1 and 2, we have review. Yep, and that's on your syllabus as well. I know there are some changes, but having the review right before your exam has not changed, okay? Oh, what type of corrosion would be the kind you commonly see on pennies, right? Well, that depends. Is it a pre-1982 or a post-1982 penny? Because the content of copper in those pennies change. There's actually a reduced amount of copper, right? So you would experience copper going to copper oxide. So you would experience copper having that, you know, reddish sheen because of plasma on frequency. And also, if it oxidizes, then it goes to copper oxide, right? So then copper goes from 0 valent to, as in copper metal, to copper 2+. So that gives you that like greenish. Copper 2+ is a greenish type of color. So that's what you observed with your eyes. So that's what one would expect if you have the penny that has copper on the outside. Okay. Does that answer your question? Okay, great. You're welcome. Any other questions? Okay, with that, I'm going to adjourn class. All right, thank you, everyone. See you. Thanks. You have a good rest of the year as well. All right, I'll see you all Wednesday. Just, I won't be giving the lecture, so. Oh, okay. Later. What should we expect more material from the new, you take care as well, from the new material or even amount from all materials? Yeah, so I updated the guide and resources page for exam 3 to denote that that all the chapters will have equal coverage, so an even amount from all the material. So exam 3 won't be weighted in some disproportionate amount. Does that answer your question? Okay, great. All righty. Have a good day, everybody. See ya.